Well, thanks you all for the introduction. So my name is Cesar, and this is joint work with my supervisor, Billy Brumley, in Tampere University of Technology in Finland. So probably the title doesn't tell you much, but I will try to make it interesting for you. So first, the outline, what I'm presenting. So I'm going to briefly discuss what's enabling cache timing attacks. Craig already talked about caches, so I can skip a bit over that. And then a bit of motivation for this work through some brief history of cache timing attacks on OpenSSL. And then I'm going to present a recipe for performing side channel attacks, very general, that you can try at home. In simple 5 steps, and then I present an end-to-end cache attack, and finally, conclusions. So, cache timing attacks, as you may know, and as Craig mentioned, they are enabled thanks to the memory hierarchy. So the memory has different levels, and as we go down the memory hierarchy, then we have different access times. So it's much faster to access the processor registers compared to L1, L2, L3, physical memory, and solid state hard drive. So due to this difference of accessing this memory, we can exploit this and perform cache timing attacks. So I have to send that. So I'm going to give a brief history of cache timing attacks on public key crypto in OpenSSL. This is very specific. So there are several attacks I'm not mentioning here because they are not cache timing attacks. So they are just timing attacks, or because they attack some symmetric key crypto in OpenSSL. Okay, so in cache timing attacks, everything started around 2005, when Colin Percival performed a nice cache attack on RSA, where he recovered the exponents using a evict plus reload attack and the L1 data cache. So that was in OpenSSL version 197. You have the OpenSSL version to your left, and then the year down there. And the crypto system, it's categorized by color. So after that cache attack, Achimes came with different research about how to exploit simple branch prediction. And he attacked the L1 instruction cache and the L1 data cache. So he did different attacks in there. He focused on the modular inverse operation used in RSA, and he recovered secret key used there. And then in 2009, Billy and Risto, they performed L1 instruction cache attack using the prime and probe technique to recover secret keys of ECDSA. So this was one of the first attacks on ECDSA. They showed that it was possible, and for their attack they used thousands of signatures to be able to recover the secret key. So after that, Achimes did the same again, but for DSA, he used prime and probe technique, attacked the L1 instruction cache, and then he was able to recover secret keys. Again, this was using around more than 1,000 signatures to recover the secret key. And then in 2014, Yuval and Katrina came up with the flush and reload technique. This opened the opportunity to attack, to make the attacks better and to attack different implementations. So after they introduced this in 2014, there were some other attacks happening. So it was Yuval's work. And so they used the flush and reload technique, which target the last level cache or the L3 cache. And they attack a binary field curve, the SEC P-256 curve, which is used by Bitcoin. And also they introduced the performance degradation attack in combination with the flush and reload to give better granularity to the attack. So this came in a very short period of time, 2014, 2015, and allows to recover the secret key using much less amount of signatures. So we went from thousands of signatures to hundreds of signatures, and then even 50, 20 signatures by now to recover secret keys. So that was DSA. And this is the performance degradation attack in 2016. Alan, Yuval, Billy, and some other folks work on that one. So they pair a performance degradation attack with a flush and reload. This allows to slow down the computation time and gives better granularity to performance cache attack. Then last year in 2016, Yuval, Billy, and I, we performed a DSA, a cache attack on DSA, on OpenSSL, using the flush and reload and performance degradation. And also, Yuval and et al. Did a cache band collision attack on RSA L1. This was interesting because he did the research and attacks on RSA stopped in 2008, and then last year, again, 2016, began. So this is a brief history of attacks on cache attacks on OpenSSL. And due to these attacks, OpenSSL had to introduce different, had to implement different countermeasures to prevent this. So now I'm going to talk about some relevant changes. First of all, in 2005, they introduced this bn flag exponent constant time and the method that performs modular explanation in constant time. This was due to the work of Colin Percival. So this constant time implementation made possible to protect RSA exponents. Then in 2007, due to the work of Alchimes et al., they introduced the modular inverse no branch method, constant time big number division, and they renamed the previous constant time flag to just bn flag constant time. So because the flag was not used only for exponentiation, it was also used for modular inversion. So this created a huge mess because first they had to identify all the places where they had to use this flag, where they were dealing with secret information. So they had to track all these places and then mark them and just make some kind of branch there to send them to the proper constant time implementation. So that was in 2005. In 2007, they had to, again, do the same and locate all those places, but now using modular inverse. And then in 2012, with the widespread use of the NISP curve, NISP P-256, they had to implement the constant time scalar multiplication for that curve. And for that, they use a fixed window algorithm, and they use masking to protect. So this was rather safe, and up to this point, the research shifts to SIG P-256, which is the Bitcoin curve, because this curve implements scalar multiplication using a sliding window algorithm. So it was easier to attack this than the fixed window and the masking. So the research shifts in here, and they start attacking different curves. And then in 2015, Shea, Garon, and et al. Implement this NIST C256 method in OpenSSL, which I think no one really knows what's happening there, but it works. And also they implement modular inversion through exponentiation using the Fermat's little theorem. So everything looked pretty much good at this point, and everyone believed that NIST P-256 curve was secure in OpenSSL. Everyone is using it by now, and if not, well, you should, or at least secure version of it. So this is the motivation behind this work. After this, I'm going to introduce a general recipe that you can use for side channel attacks on digital signatures. For the recipe, first you take an algorithm that uses confidential data, any algorithm that is used on crypto, and then you can measure the side channel leakage. For that, you can use any channel, acoustic channel, electromagnetic channel, cache, any channel you want. And then you run your data through a signal processing machine, like black box signal processing. And this turns the data into a sequence of operations. So let it be squares and multiplies, or doubles and adds, you name it, depending on which algorithm you are attacking. Once that you have the sequence of operations, you convert this sequence to bits. And these bits are combined with messages and signatures. All this is put into a lattice. You let it run for some time, maybe some days, depending on your lattice. And after that, you have the private key. So that's the general idea how side channel attacks work on digital signatures. So now I'm going to go through all of this quickly in our attack, how we implement it. So our primitive was, we attack ECDSA, NIST P-256 curve. It's defined by that equation and those parameters. So it's a curve, a hash, base point, the secret key, and the prime modulus. Yeah. And signing, a signature is given by R and S. R is computed by multiplying a nonce k by the base point, modular n. Here, this has been exploited. Okay, so we have note that the nonce k is recoverable if at least 3 bits are leaked for each signature. So you have many signatures, and if at least 3 bits are leaked for each of them, you can recover the nonce k, which leads to the recovery of the private key. So when you create a signature, R multiplies the nonce k by G, and that's done by a constant time scalar by point multiplication. So this has been exploited several times already. So what we looked was for some other place where we can exploit the k, and we saw this modular inversion of k, and we decided to take a look how is it done. So we went through the code. It looks messy, but basically it's a modular inverse method in OpenSSL. There it checks if the flag is set. If it's set, it should go to the modular inverse no branch, which is the safe version, and if not, then it continues. The problem is that the flag is not set, so it never goes there, and it continues with the normal implementation. So that's great for us. The normal implementation is the binary extended Euclidean algorithm. This has been proved to be highly dependent on its inputs. So we can recover this information from the algorithm. The number right shifts on V, the number right shifts on U, subtractions on V and U. V and U are inputs, which is the nonce k and the modulus p or n before. And also we know some other facts about it. Only one loop per iteration is performed. And U loop is the only loop that can execute it at the first iteration. And we know that the K should be protected in OpenSSL. It should be padded. But we noticed that it wasn't. So first, during our cache attack, we put a probe on this method, bnrshift1, to track the write shifts, and another probe on bnusub to track the subtractions. And we saw that those facts were indeed happening. And then we saw that the K is protected, the nonce, but the moment it goes into this method, it's reduced modulus n, so therefore the padding doesn't work at all. So to measure the side channel leakage, we use the flush and reload. So I'm not going to go too much into it, but basically the victim executes its process, fills the cache, the attacker flushes the victim's data from the cache, waits for some time, measures the time, and then waits for some time, and then reloads the data, and again measures the time, compares the difference, and that's the latency. So that's pretty much how it looks, the cache, very raw. So this is the sequence of operations of shift and sub. You can see clearly, maybe, when it was R shift and when it was a subtraction. But this is very raw, and it's very difficult to get much information out of it. So we are losing some information in there. So to help us with that, we came up with an improved performance degradation attack. So this allows us to identify better addresses to probe and better addresses to degrade. So first thing we do is we identify candidate methods for memory addresses. We have all these methods used during the computation. We get the addresses, and then we start degrading one memory address at a time. And at the time we do that, we measure using performance counters how many cache misses and clock cycles are happening there while we degrade one address at a time. So this way we can find the best combination of addresses to degrade and to probe. So we pair the performance degradation, with the flush and reload attack. This is our setup and attack scenario. So we use an Intel Core i5, Sandy Bridge, 8 gigabytes of memory, running the latest version of Ubuntu at that time, and OpenSSL 101U. So we have in one core the victim, in another core the spy running, probing, and in two cores we have to performance degradation processes. OpenSSL is sitting in the last level cache, where it's a shared library, so that allows to perform this flush and reload attack. So we apply some signal processing to the data we received. First we template and use cross correlation to identify where the operation starts and extract from the whole sequence only the part that we are interested in. We apply some moving average, and then we go from a raw trace to a better, cleaner trace, which is easier to use. And then this allows to transform this trace to a sequence of operations. In this case, shifts and subtractions. Unfortunately, it's not a straight way to transform the sequence to bits. That's not how it works in this case. Before it used to be that simple, but not anymore. So we have to come up with an idea how to recover bits out of the sequence of operations. So to do that, we created a whole bunch of sequences, and then we were aiming for 3 bits. So we saw that taking sequences of length 5, we could just get at least 3 bits. So at the beginning, looking at these patterns, we could recover this amount of bits with this integer value, the one under AI, sorry. So we did this for length 5, and then we checked different sequence lengths, and we saw that after length 7, basically we're not gaining much because the minimum bit we could recover was 4. So we decided to stick with lengths 5 and 7. We created these tables of how many bits we recover and what's the actual decimal value of it. And then we plug this into a lattice attack. So we input the bits, the messages, and the signatures into the lattice attack. And these are the dimension D+2. It was implemented in Sage using BKC reduction. Our work, we use at least 50 signatures. Dimension was 50 plus 2, 52, and we managed to recover after 80 minutes the secret keys. So they were fairly good results compared to previous work, where the signatures were much more, even though the dimension was smaller of the lattice. And after that, we decided to apply this to an end-to-end protocol attack. So basically what we did was we analyzed the algorithm offline. We created the spy and degrade processes offline, and then we went to a server. We put them there, let them run, and start capturing TLS and SSH connections. So these protocols perform digital signatures, and then we send this information back to our host computer, and then there we process everything, and we recover the secret keys of servers running TLS and SSH. So after all that, well, we all know that crypto libraries are a prime target for cache timing attacks. We offer a patch to libraries. OpenSSL 101 reached end of life at the beginning of this year, so they didn't took our patch. They cleaned their hands and they said we don't offer support to this anymore. Boring SSL had this issue in 2015, but it wasn't an issue anymore when we found it. And LibreSSL, they quickly apply our patch. So this is an issue because OpenSSL, even though it's not the latest version, it's still shipped with Ubuntu long-term versions, Debian and SUSE as well. So you should upgrade to 102 or 110. If you can't, then at least apply the patch that is in our paper. And in conclusion, constant time implementation need to be tested, and especially flags, as David mentioned, they are not tested all the time. Binary extended clean algorithm, it's highly dependable on their inputs, so it shouldn't be used. Performance degradation techniques are really useful for cache timing attacks. And different key bit recovery approaches are possible, even though it's not always straightforward. And well, as you saw, the cache timing attacks are getting very popular and they're increasing complexity every year. So, yeah. Thanks very much. Take questions.
Any questions? I have a question.
Yeah.
You mentioned that when they do the K doesn't have the constant time flag, right? That's the cause of the problem.
Yeah.
If they had it, it would have solved the problem.
Well, that's the easiest problem because it goes to the no branch option of the modular inversion, which they say it's constant time, but it hasn't been proved, so it's possible that it's not.
Okay.
Yeah.
And that's the solution they have for 102?
I think for 102, yes, and in the latest one they use the modular inversion through exponentiation. So they no longer use different algorithm to invert.
Okay.
They use exponentiation. More questions? Well, thank you very much and enjoy your lunch.